Hello. This will be a demonstration of proposition 14 from book 9 of Euclid's Elements, which says that if a number is the least number which is measured by certain prime numbers, then there will be no other prime number which measures it. We're going to have some number a, and a will be the least number that is measured by b, c, and d. And what we want to prove from this is that there is no other prime number except b, c, and d which measure a. For if this is not the case, then there will be some prime number e which measures the number a and is not the same with b, c, and d, is not equal to b, c, and d. We're also going to create the number f such that the product of e and f is the number a. We know, of course, that the number f does exist because the number e measures the number a. That's how we made the number e. Now, we know the prime number b measures the number a. We were given that. And what we know from proposition 730 is that if a prime number measure any number, and that number is the product of two numbers, then the prime number will measure one of those two numbers. So the prime number b measuring the prime number a, and a being equal to the product of e and f, we know that the number b will measure e or f. But we know the prime number b does not measure the number e, for the number e is also prime and is not equal to the number b. So because b does not measure e, b of course has to measure f. It has to measure one between the two of them, so if it doesn't measure e, it has to measure f. We can prove in a similar way that the two other prime numbers c and d also measure the number f, so that our three numbers b, c, and d all measure the same number f. But we know from our given that the number a is the least number which is measured by b, c, and d. So we know that the number f has to be greater than the number a because we know the number a is least. But we also know that the number a has to be greater than the number f. We know this because a is equal to the product of f and e. So f has to be less than a. So a is greater than f. But we just proved in the previous step, step 6, that a is less than f. So what we have to say is that the number a is both less than and greater than the number f, which is obviously impossible. And so what we can conclude is that there is no other prime number which measures the number a, which is what we set out to prove, which means we're done with the proposition, therefore, etc., q, e, d. An example of what this proposition might look like is, say we have the number 30. Now, the number 30 is the least number that is measured by the three prime numbers 2, 3, and 5. We know that 30 is the product of 2, 3, and 5. 2 times 3 times 5 make 30. That's easy enough to verify. 2 times 3 makes 6. 6 times 5 is 30. 3 times 5 is 15. 15 times 2 is 30. And 2 times 5 is 10. 10 times 3 is obviously 30. What this proposition is going to tell us is that there is no other prime number except 2, 3, and 5 which measure the number 30, and that's easy enough to verify. 7 doesn't measure 30, neither does 11, neither does 13. You can keep going down the line, and you can show just by brute force that there is no other prime number that measures 30 except for 2, 3, and 5. One last thing to note about this proposition is that this will also help us prove the fundamental theorem of arithmetic. I mentioned this at the end of my previous video. What that theorem states is that every composite number is equal to a unique product of prime numbers. So how this is going to help us is that 2, 3, and 5 only make up 30, and that there is no other set or product of prime numbers that make up 30. This is going to help us prove that fundamental theorem of arithmetic. Again, Euclid doesn't prove that, so we're not building up to that in book 9. We're building up to two other things, which I'm excited to present. But perhaps sometime down the road, I'll demonstrate the fundamental theorem of arithmetic. That being said, I'll end the video here and move on to proposition 9.15.